In this lesson, what we're going to do is work this problem in 3 dimensions. I know it looks really, really ugly and messy, but really, if you focus on it, it's not too bad. What we have is a circle of some kind. You can think of it as a ring, or a marble, or some kind of spherical object. And it has a weight to it, so it's 900 newtons oriented down. And it's also acted upon by 4 additional forces here in red. And one of these forces goes in the x-axis and is 600 newtons, but that's the only other force we know about. All of these other forces are, we know the directions from the drawing, but we don't know how strong they are or how much force they are. In fact, that's what we're trying to find. What is F1, F2, and F3 in terms of newtons? That's what we're trying to find out. So ultimately we have an equilibrium equation here. We're saying this guy doesn't move. What are these forces? Now, the tricky thing about this is 2 things. First of all, the drawing is drawn in such a way to convey a lot of information. You're going to see this a lot. For instance, F sub 2 points purely along the negative x direction because you can see the dotted line coming out of it, which intersects this way. F1, if you look at the dotted lines here, it lies in the plane of y and z. There is no other components other than y and z, so it lies in this plane. The most complicated one extends in 3 dimensions. You can see F3, and the way it's drawn is, you can see, they'll talk about the triangle in a second, but it goes up and then a projection of this vector lies down into this plane. Now notice the triangles. We've seen the triangles all over the place in mechanics. They're just giving you the angle without really putting the angle on the paper. And I don't know why some books like to do that, to be honest with you, because in real life you're not going to see that, but they want you to kind of flex your trigonometry muscles a little bit. So when you see 3, 4, 5, it's basically giving you the angle of the vector. And so this guy is 3, 4, 5 giving you the angle that way, 3, 4, 5 is giving me the angle up, and then we have an angle related to the projection of this vector down into the xy plane. This is what this is supposed to represent. So our goal is to figure out a way to represent these 3 vectors in Cartesian form, and then we'll add them to the 2 known vectors, and then hopefully we have a system of equations we can solve for each of these unknowns. So we should end up with 3 answers, F1, F2, and F3. Now before we actually go on, I want to take a little aside for you. So I'll say recall here. Recall. Let's talk about this 3, 4, 5 thing a lot. I've kind of glossed over this a few times, but I want to kind of talk about it with you. If you have some force here, okay, and if I give you something like this, if I draw something like this and I say 3, 4, 5, I've told you several times that I'm implicitly giving you the angle in here, and what I mean by that is basically if you want to know which way F points, this information is encoded into these sides. What it's telling you is that if you go 3 units over and 4 units up, then this length on this side would be 5 units, and that's locking in the angle that F points. In fact, it's the same as basically giving you this angle here. So instead of putting the angle on the drawing, which is actually kind of hard to do in 3-dimensional drawings anyway without getting cumbersome, you see these little triangles someplace. Now let me recall, or kind of work with you here a little bit in trigonometry. If I wanted to find what this angle is, how would I do it? Well, I would say, there's several ways to do it. I would say the cosine of this angle is the adjacent side over the hypotenuse. So the cosine of the angle is 3 over the hypotenuse, okay? And likewise, I can also say that the sine of this angle is the opposite side over its hypotenuse. This is all straight from trigonometry, okay? So what's happening though is typically I'm trying to figure out what the components of F are a lot of times. I'm just trying to figure out what's the x component, what's the y component. So if I'm trying to find the x component of F, pretend that I knew what the angle is. Pretend that I knew that this was 35 degrees or something. How would I find the x component? Well, I would say that the, let me draw a little line here. I would say that the x component of F is just F times cosine theta. Let's pretend I just know what theta is. F cosine theta chops it down in the x direction. And likewise, I would say that the y component of this force is F times the sine of theta. This is just basic components, basic trigonometry. But notice that I already know what cosine theta is. It's 3/5. So really, the x component of this vector is just 3/5 times F. You know, this 3/5, I just put the number in front. And the y component is, this becomes 4/5, so it's 4/5 F. So do you see where we're going with this? When you're given these little triangles in here, you can write the x components in terms of fractions of the entire tension or whatever on the line. So the way I like to do it is kind of old school. I would like to go back and actually figure out what this angle is. And once I calculate what the angle is, then it's f cosine theta, f sine theta. But you have to find what the angle is first. And if you have 3 or 4 vectors, and you have to find the angle of all 3 or 4 of those vectors first before you can do the cosines and the sines to get your components, okay? What I'm trying to tell you is if you carefully look at your drawing, you can figure out what the x component is just by fractions, 3/5. It's like the x component is this horizontal component compared to its hypotenuse times f. Same thing for the y. Y would be the vertical component compared to its hypotenuse times the guy. So as you're writing your component equations and you're given a lot of these triangles, it's actually a lot faster just to use the values of the triangle they give you. So when you see solutions in your textbook, like examples or whatever, and you have all these fractions everywhere, sometimes you go, what is this coming from? It's just the cosine and the sine. That's all it is. Okay, so now we want to move along. Okay, and we need to find vector representations of all of these unknown forces. So first of all, let's go to F1. F1 vector, what is that going to be written as? Well, it has a y component and it has a z component. There is no x component of this guy. So if I want to find the y component of this guy, it's going to be what? Usually if I know the angle, it would be f times the cosine of this angle. But like I said before, I really don't have to do that. The way I can rewrite that is I can say F1. Well, let me just rewrite it just to make it totally clear for the first time. F1 cosine theta, that will be in the j direction, plus F1 sine of theta, and that'll be in the k direction. If you look at this, this angle here is, if I take the cosine, I'm going to chop it down and get the y component. If I take the sine, I'm going to get this. But I don't really need to actually find out what these angles are, because really cosine of theta, you can see, is F1. Cosine of theta is going to be this guy, 4 over 5. So what I'm going to get is 4 over 5. This is in the j direction, plus F1. The sine of theta is, again, the vertical part divided by 5, 3/5 in the k direction. This is a 5 here, 3/5. So you don't have to go finding what these angles are and then taking the cosines and the sines. You just can use the fractions if you're given one of these little triangle deals. Okay, so this is essentially what vector 1 is. Again, I don't know what it is. It's really unknown what these magnitudes are, but at least I've made some progress. So what would be F2? F2 exists purely in the negative x direction. Look at the way it's pointing along this dotted line. So for F2, it's basically going to be negative x direction, the magnitude of whatever is on there in the I direction. Negative I direction means negative x direction. So it's a pure vector. I don't have to do any trig or anything because we know which direction it's pointing. It's pointing in the negative x direction. The magnitude's F2. So that's the vector form of force number 2. Now, what about force number 3, or line number 3? F3. Okay, this is actually the most complicated of all of them when you really look at it. Now, I might blow your mind a little bit with this if you haven't seen it done before. Hopefully you remember a little bit of calculus. When we do three-dimensional calculus, you see this kind of thing a lot. So if you've been a while, this may blow your mind a little bit. But basically what we're trying to do is we're take this arrow, we're trying to find out how much of it exists in the x direction, how much of it exists in the y direction, how much of it exists in the z direction. And we have actually 2 triangles. One triangle is up here, and the other triangle is really related to the projection of this into this plane, the xy plane down here. Notice that this dotted line here is really just the projection. If I were to put a flashlight up here and shine it down, the shadow would be the dotted line that lies in this plane. And now I have the 3, 4, 5 triangle that governs that down there. So if I want to find the x component that lies along here, first I'm going to chop it down into this plane. How would I do that? Well, I'm going to say it's F3. I want to chop it into this plane down here, so I'm going to say 3/5. That's basically taking the cosine of whatever angle this would form with that axis down there. So put 3/5 here. Now this guy, F3 times 3/5, that just gives me the length in the xy plane. I've chopped this down and found multiplied the hypotenuse times the cosine, giving me this here. Now how do I get the x component? I need to take this and chop it to make it in the x direction. So it's going to be 3/5 again, multiply by 3/5. It looks a little bit weird that you're taking 3/5 times 3/5. It only looks weird because these triangles happen to be the same. This problem was chosen to be a little simpler for you to understand, so the angles of everything are kind of nice angles. This triangle happens to be 3, 4, 5, and this one happens to be 3, 4, 5. Okay, now that is going to exist in the I direction. Now in the J direction, which is the Y direction, what's it going to be? It's going to be, again, take the projection down into this axis, so it'll be F3 times 3/5. The 3/5 coming from here and here, that chops it here. Now I want to figure out what the component is on this direction, the component of this projection along here, so it'll be 4/5. That's basically like taking the sine of the angle in that plane there, 4/5. Now notice though, that because of the way it's drawn, the y component is pointing in the negative y direction. So to take care of that, I'm going to put a negative sign there, right? And then I have j. Now what do we do for the k direction? This vector, I don't need to chop it into this plane anymore. That's just to give me x and y. To figure out what the k component is, it's just 4/5, because that's like taking the sine of this angle, projecting and getting me this guy, which is 4/5. So what it's going to be is F3 times 4/5 in the k direction. I really do need you to study this until you feel like you'll understand what I'm doing. It's no different than in calculus when you're given a three-dimensional vector or something and you have to find the components. Typically in calculus it's written as magnitude times sine theta cosine phi, or sine theta sine phi, something like that, because we define different angles and then we take cosines and the sines. Really, I'm doing the same thing. To get the x component, I'm first chopping this to get it into this plane by saying 3/5, which is like taking the cosine of this angle. And then once I have it here, to get the x component to sweep it that way, again it's 3/5. To get the y component, I chop it down here. Once I get it down here with 3/5, it's going to be 4/5 to give me this y component. And to get the z component, I don't need to chop it into this plane at all. It's just this times what would be the sine of this angle, 4/5, the vertical component of it. But in any case, this is basically the answer, but we can simplify just a little bit. We can say the F3 vector, it'll be F3 times 9/25 when we do this multiplication in the I direction, minus, it'll be F3 12/25 in the J direction. Okay, and then finally we'll have 4/5 in the K direction. All right, so those are those guys here. And also, don't forget that we have a couple of additional vectors here. We have, and I will just write it down over here, we have 600 newtons purely along x. So we have another force vector, which is 600 purely in the x direction. And we also have the weight of the object, which is 900 newtons purely in the negative z direction, so negative 900 k. These are purely along x and negative z, so we can just write them down. We don't have to do anything fancy. We have to deal with the angles to get all the mixture of components for these other guys. So now, all of that discussion was simply to get a vector representation of all of the vectors in the drawing. So you have to do a little bit of work there. Now, we just say that the sum of the vector forces has got to be equal to 0. So let me draw a little squiggly line. And we will do that. We're going to add them all together. So first, let's just start with this one. 4/5 F1J, 3/5 F1K. So what we have is 4/5 F1J plus 3/5 F1K. All right, which is this guy. And then after that, I'm going to be adding this guy here, the F2I. So minus F2 in the I direction, okay? And then I'm going to add this vector, this and this and this. I'm just going to add it all in there just as we go. So I'm going to have 9/25 F3 in the I direction minus 12/25 F3 in the J direction. And then I'm going to go on the next line and I'm going to say plus 4/5 F3 in the K direction. So that's the third vector. So now I've added this vector to this vector to this vector. Don't forget I've got a force of 600 newtons along I plus 600 newtons in the I direction, and then I have a weight of negative 900 newtons in the K direction. All of those things have to be equal 0. Basically, I'm just taking all of the vectors and all the components and all of their glory, and I'm adding them all together. And I know it looks a little bit messy, and it is a little bit messy, but ultimately when you have a vector equation like this, all you're doing is you're saying I'm going to add all of the I components together, and they have to equal 0. I'm going to add all the J components together, everything you see with a J, and they have to be equal 0, and so on. So for the I direction, let's just go along. That's not I, here's an I. So for reasons that will become apparent in just a minute, I'm going to kind of give myself a little bit of space, and I'm going to say negative F2, which is this guy. And then, so I'm going to put a little dot probably under here to signify that I've tackled that one already. This guy is next, so I'm going to have plus 9/25 F3. That's in the I direction, so I've taken care of that one. I keep looking for anything along I, and I'm going to have 600. So I can add plus 600, but typically you want all of your constants to be on the other side, because ultimately you're going to type this into a solver, so all the constants go on the right-hand side. So I've taken care of that in the I direction. Then we go down here and say, hey, let's look at everything in the J direction. Here is something with F1, so I'm going to write that over here, 4/5 F1, okay? And then I've taken care of that, so I'm going to look for anything in the J direction. Here's something else in the J direction, and it involves F3. So I'm going to skip a space, and I'm going to write it like this. You'll see why in a second. 12/25 F3. So that's this guy in the J direction. Anything else in J, there's nothing else there, so it's just equal to 0. Okay? And then finally in the K direction, I'm going to go looking for this. I've got 3/5 F1. 3/5 F1. I don't need to put the K down. We already know we're going in the K direction. We go continue looking over here. Here we have plus 4/5 F3, so I'm going to skip a space. It's going to be plus 4/5 F3 in the K direction, like this. And then I have 900 in the K direction. This is just a constant. I could subtract 900 and set it equal to 0, but all of the constants you typically want to put on the right-hand side. So this is my set of equations. Look how I've written it down. I've written it down in a weird way. This is one equation, this is one equation, and this is one equation. The reason is because the number one problem people run into when solving systems of equations like this is you actually type it into your calculator wrong. And it's a real pain. So whenever I write now if I had all three variables in all three equations, it would be easy. I would have everything lined up. But you want to have your system written down with the same variables on top of one another, and you want to have your coefficients easy there to see. So really the system of equations, if you really think about it, really is saying 0f1 minus f2 plus this. This one's saying 4/5 f1 plus 0f2 minus this. And this one's saying 3/5 f1 plus 0f2 plus 4/5 f3 is equal to this. Now when I kind of filled in the blanks, you see why I did it. This is a column of f1 variables. This is a column of f2 variables. This is a column of f3 variables. All of the coefficients are easily identified. There's 9 coefficients, and then all of the constants are on the right-hand side. So now you can solve it any way you want. You can take this as a matrix, a 3x3 matrix, inverse the matrix, multiply by this column matrix. That's going to solve for f1, f2, f3 right away. If you want to do substitution, if you want to do something else, go for it. If you want to type it into a solver, you need to make sure that you put 0, -1, 9/25, 4/5, 0, -12/25, and so on, if you're going to type it into some kind of matrix solver, because it needs to know what's 0 and what's not. So that's how you would type the system in. When you do all of that stuff, you're going to solve the system of equations, and what you're going to get is F1 is 465.5 newtons, which is pretty close to 466 newtons. And you'll get F2, 879.3 newtons, which is pretty close to 879 newtons. And then F3, 775.8 newtons, which is pretty close to 776 newtons. And these are the answers, okay? Again, I'm not going to go through the algebra to solve this because you're in engineering class and you can solve these things yourself manually. More likely you're going to use a calculator, and that's totally legal to do at this step. Believe me, if you don't know what you're doing, you're never ever going to get the right set of equations right to even get to the answer. So almost all of the credit is in figuring out how to set these equations up. So we didn't have to draw a separate free body diagram because this was kind of already done for us. It's a point there and there's forces. All of the magic of this problem is realizing that you have to write these force vectors down, and the trickiest one was this one because it extends in all 3 dimensions. So when you have these weird little triangles, you have to find the projection of it into this plane, and then you take that projection and go x and y with it. That's why we have these 2 fractions multiplied together in a couple of places. Once you have the representation, you literally add them together vectorially, which means you add them component by component, and that's what you're doing. That's what yields the system of equations that you solve. You really need to get used to doing this kind of thing, because although we're just doing static equilibrium now, we're going to get into all kinds of other things with rotations and moments, but ultimately they're all going to lead to systems of equations. So get comfortable with solving them. Get comfortable with using your calculator. Get comfortable with writing them down and not making mistakes and keeping your signs in place. When you do that, you'll get that practice that you need. Follow me on to the next section. We'll do one last problem with static equilibrium of particles in 3 dimensions. Learn anything at mathandscience.com.